let's go ahead and get started. Again, thank you so much for taking some time out of your busy schedule. I just want you to know that I know how much your time is worth, and I want to bring content to you that's valuable, relevant, interesting, and I hope that you learn something along the way. I'm going to be presenting a little bit. However, the featured presenter is a colleague of mine by the name of Alan Ross. Alan Ross is a consulting system engineer here at Cisco. Alan, say hi.
Hi, everybody.
And Alan's going to be driving the presentation. Now, he's going to be driving it simply because much of what we're going to be looking at today is demonstrations. We're going to jump right into the tools and into controllers and show you what we're going to be talking about. But today's topic is HDX. And I won't use acronyms that I don't define. So HDX is just simply Cisco High Density Experience, which kind of sounds like architecture, a little bit marketing-y. Yeah, I know it does. However, really what HDX is a bunch of either pre-standard or proprietary or whatever name you want to give to it, features that we put into our environment that don't necessarily come with all access points because they're not part of the standard yet. And even still, you'll see. In fact, if we go to the next slide, Alan, we're going to look at a bunch of. Oh, you know what, Alan? Let's hit your disclaimer first, please.
All right. So yeah, real quick, I just want to touch on one thing. You guys have all gotten the golden ticket today to experience and see how to configure our HDX features. With great feature comes great responsibility. And one thing we don't want you to do is just roll these things out into a production network. Please get these in a lab environment first, or at least in a limited deployment, to understand how these changes and how these features are going to impact your clients and your wireless clients' connectivity to the network. Under almost every circumstance, these features will not fix any bad implementation. So I want to underscore that today and make sure you understand. Bad implementations need to be fixed first before we start getting into some of these features, but keep those things in mind as we go through this.
Great. Thank you very much. Good points. So we're going to be talking about a number of things. In fact, there's 7 of them here, and we'll waste no time getting into the meat of what's going on. But you can see that there's a lot of acronyms. We'll be defining all of them, and we're going to be talking about what makes HDX so interesting. And we're going to start with custom access point hardware and what the marketing guys call turbo performance. I think it's the worst sounding name, so I gave it a similarly cheesy looking slide. But when we take a look at how access points are made, typically access points have they have a CPU and RAM, and they have an operating system, and attached to that is a 2.4 gigahertz radio and a 5 gigahertz radio as interfaces, obviously not listed here as an Ethernet or fast Ethernet or now gigabit Ethernet interfaces. This is a traditional design for an access point. Now, if we wanted to do some really cool stuff, we might have to put new radios in, but we don't actually do that. One of the things that we do is we put a dedicated CPU and RAM for each radio. And what that allows us to do is pre-process a lot of the RF-related data before sending it into the centralized or common CPU. But here's an interesting thing. We don't even stop there. In our new Wave 2 access points, we have beefed up the CPU with a dual 1.8 gigahertz dual-core CPU with a 5 gigabit backplane networking subsystem with hardware offload, which basically means it has this similar ASICs that we have in our Ethernet switches. We double the RAM. We put faster processors on the radios. But notice that we have that 5 gigahertz radio. But notice above that, it's not a 2.4 gigahertz radio. It's actually called an XOR radio. It's a software-defined radio that allows us to switch between a 2.4 gigahertz radio and a 5 gigahertz radio. That's going to be something really interesting we'll see in just a couple of minutes. Attached to that, we have the ability to have some specialized antennas. And then we also have on our 3800 series access points an expansion slot for future expandability, not necessarily, but not excluding, new Wi-Fi technologies, but also including some really cool stuff that will be announced really soon. So we have some expansion slot capabilities as well. So that talks about turbo performance, and you know, so again, a little bit of a marketing sounding name, but hardware does matter, and our access points are different than other. A couple of people, by the way, asked a question. The XOR radio, is it only available on the 2800s and the 3800s? And today that is true. Yeah, the 2800s and the 3800 Wave 2 access points are the only access points where we have this thing called flexible radio assignment, which is the very next thing that we're going to be talking about. So moving on. Flexible radio assignment is really good. Alan, can you walk us through, please, an example of what flexible radio assignment does for us?
Yeah, so when you pull the ASPs, specifically the 3800 and 2800 out of the box, their default configuration is going to be a 5 gig and a 2.4 client serving radio. With FRA disabled on your controller, that's the state these APs will stay in until we enable FRA. Once FRA is enabled, that allows the system to analyze the environment to determine redundant radios and then make a suggestion or automatically make a change to those redundant radios to pick up certain areas and cover them better, maybe in 5 gig, or switch a radio to monitor mode to give you more visibility into the spectrum of the area while still making sure that you have coverage in the 2.4 spectrum. Some points to make note of in the current shipping release of code is that FRA detects and identifies just redundant 2.4 gig radios. It does this through a process we call coverage overlap factor. It's a calculation that's performed on the controller. All of the APs within an AP group are contributors to the coverage overlap factor of the APs in that group. So if I have two APs that are adjacent to each other that are in two different groups, the coverage overlap won't be calculated between those two APs. So it's only within the APs within the AP group. All 2.4 gig radios participate in this coverage overlap calculation. So not just your 28 and 3800s, but all of your legacy 2700 and 3700, 36 and 2600 APs, all that 2.4 spectrum coming out of those radios are actually calculated as part of this. However, only the 2800 and 3800 access points are the ones that can switch their radio roles. You have an option for your sensitivity threshold to determine when you want to make the change to the radio role. So low being 100% coverage overlap, medium being 95% coverage overlap, and high being 90% coverage overlap. We don't usually go much lower than 90 because then you won't have coverage in the 2.4 spectrum. Once the radio has been determined redundant, DCA can make the change to the radio role if you have it set up for auto. And there's two assignment methods now, which is auto and manual. Auto will do the calculations, and then DCA will make the change, obviously. And in manual mode, no changes will be made. However, we'll still do the coverage overlap factor calculation so that you can see how much coverage overlap that you have. Now, this is the recommended best practice role we suggest you put the APs in out of the box when you turn on FRA. The reason being is you don't want FRA going and making a bunch of changes when you don't understand what's happening in the environment before those changes are made. So let's go ahead and jump right into what this looks like and how to configure this. So I have a controller here. And I want to make a point before we begin. On my controller, I'm running the current CCO build of 8.3 MR1. So you may or may not see some things on your controller code that you see in mine here today. So with that, let's go and do the first best practice thing, which is go and set these APs into manual mode since we have not turned on FRA yet. So there's a couple different ways to do this. One is through the GUI, and so you can see it here. I have two 2800 APs connected to my controller, and so I will go over to the very left-hand side under access points and go to my dual band radios. And under here, I'm going to go to one of these 2800s, and on the very right-hand side, you'll see the caret, the blue caret. If you hover over it, you'll get a configuration option menu there, and I'll select that. And in here, you'll see the ability to change the role assignment. So you have the option of auto and manual. And then if you're doing manual, you have the option of doing client serving or monitor. And under client serving, you can choose 2.4 or 5 gig. For our purposes today, again, best practice, we're going to leave these APs in manual mode. Now you're going to say to me, Alan, I got 100 APs. I don't want to have to go into each one and do that. All right, good. Let's go into the CLI and let's take care of that. So we have a command to be able to do it in batched for all the APs connected to your controller. So here I've got my CLI. I'm going to type in config advanced FRA revert. And then I have some options to revert. Specific ones are all AP, so I'm going to choose all. And then the next option is going to be either static or auto. So static will set them into manual mode. So all APs connected to my controller will now be placed into manual mode. Consequently, if I wanted to, let's say we had APs deployed and we left them in auto and it made a bunch of changes and we wanted to do it all over again, we can run this command using the auto command, right, instead of static. And that will reset all the APs back to out-of-the-box settings with 5 gig and 2.4, and it'll recalculate everything and start the whole process over. So today we're going to do static. I'm going to hit enter. It's going to give me the usual. It's going to disconnect clients while we make this change. And so now we're good. We have all the radios on, all the APs on my controller set for manual mode. So let's go ahead and enable FRA. So that's going to be under wireless. And then we're going to go to the advanced on the left. And the first option is going to be flexible radio assignment. And you can see here, it's by default, it's disabled. So we're going to go ahead and enable it. And we have two options here, the sensitivity, which we talked about earlier, low being 100% coverage overlap, medium being 95% coverage overlap, and high being 90% coverage overlap. So once we've determined at what point we're going to make those changes, you have an option for choosing when the changes will be made if we're doing auto. So you have all the way as low as 1 hour to 24 hours. So we'll leave those where they're at and hit apply. And then once we have that done, to validate we've got FRA turned on and we're doing something with it, we go back to the monitor tab and we go to access points on the left and we'll look at our dual band radios. And in here, we'll be able to see that we have our two 2800 access points. We have them currently in the static mode, which means they're in manual mode and they won't be changing. There's 2.4 client serving. And then we also see our coverage overlap factor. So you can see here, I've got one AP that's got 100% coverage overlap. The other one has 0 and is still calculating. Now, when you first turn this on, be aware you won't see coverage overlap factor information immediately. It's going to take a little bit of time for the system to do all the discovery, excuse me, to do all the discovery and then place the values up in here and then start making suggestions on where they're going to go. But that's how you turn the feature on, and that's how you validate it. Back to you, Jason.
Love it. Thanks. That's great. So a lot more acronyms coming your way: DBS, Flex, DFS, and EDRRM. So let's get into those. DBS. So DBS stands for Dynamic Bandwidth Selection. Now, you heard this, a couple of acronyms, TPC and DCA, right? Transmit Power Control and Dynamic Channel Assignment or Dynamic Channel Allocation. These basically determine, okay, well, of the channels that are available to me, which ones should I choose? Well, with 802.11ac, we actually have the ability to not only choose a channel, but also choose a channel width. We love the wide channels, the 80 megahertz wide channels, because that allows us to get to the multi-gigabit wireless. I'm using air quotes with that, like multi-gigabit wireless. However, with 80 megahertz channels, that really limits the amount of non-overlapping channels that we have. So now if we do that without really thinking about it, we could potentially paint ourselves into a corner and create some situations that we didn't expect. But now, in order to accommodate our higher density environments, we might use 20 megahertz channels, but that limits us to how much bandwidth we can get. I'm wondering if there's a better way. Well, in fact, there is. It's called Flex DFS, and we'll look at that in just a second. Now, I love these visuals. Alan, can you walk us through what this is?
Yeah, so we want those big 80 megahertz wide channels, and in 5 gig, that means we got to go turn on that Uni 2 extended, right? But the problem with Uni 2 extended, it's such a headache because are we going to get radar hits? Are we going to have to back off the channel? This is so irritating. As a Wi-Fi guy, I don't really care. I just want my channels. I don't want to deal with this whole radar thing. Well, until I saw this, I didn't really care. But I fly planes, which probably most people do. And airplanes use weather radar to figure out where they're going to land, how they're going to land, and where they're going to fly. And this is actually real-world scenario of a Wi-Fi hit against a aircraft weather radar. It created this nice striped line. And if a pilot is unknowingly trying to avoid this, or it pops up, or it changes their flight plan, right, I want the plane to stay in the air. So DFS is really important for airplanes, and it's really important for us to make sure we're avoiding those channels. But the problem now is I've got this big 80 megahertz wide channel because I need all those Uni 2 extended. But how do I avoid, when I get a DFS hit, how do I avoid taking out the entire 80 megahertz wide channel? And so that's what Flex DFS comes in and does. With DVS in combination, we take the 80 megahertz wide channel because we think it's appropriate for the area. And when we see a radar event, let's say on channel 60, our clean air chip will detect that, know that it's specifically down channel 60 and not affecting any of the other channels, and we'll just notch out that chunk of the channels and leave the 40 megahertz wide channel in place to use. So we aren't going to take out the whole 80 megahertz wide swath of channels. We're going to keep some usable channels in place because there's no DFS hits on those specific channels. And likewise, if we find another hit on a channel further down the road, we'll do the same thing. We'll notch that one out and leave the existing channels there. So Flex DFS combined with DVS gives you the most flexibility for using those Uni 2 extended channels, as well as not notching out the whole 80 megahertz wide channel when we see a radar event on it. So the great thing is that DFS is enabled by default, Flex DFS, on all clean air enabled chips because we have the ability to see it. So you're good there. The only thing we have to show you today is how to turn on the DBS. So what we're going to do is we're going to step right into that and show you guys where to do that. So the first thing I'm going to do is show you on the home screen. So this is a screen when you first log into the controller. Allows you to validate quite a bit of information in here. And I wanted to show you under best practices that you can actually see DBS is not enabled. So under RF management, I'll expand this, and you'll see best channel width is not selected. And if we expand this, we have the option here in this menu to actually make the change and fix it here, but we're going to do that in the advanced menu today. So let's go ahead and do that. Now this is one of those features I like to set up into an RF profile. So we'll go to the wireless tab and we'll go to RF profiles. And I've created an RF profile for my 5 gigahertz spectrum. So we'll look at that, and then we will go into our RRM settings. And you'll see a lot of the global RRM settings are now available in RF profiles. If you're on older versions of code, some of these things may not be in here, and we've added more with each release of code. What we're interested in today under DCA is the channel width. So right now we're at 20 megahertz wide. We have the option to manually select 40, 80, and 160, but we're going to select the best today and go ahead and apply that. Now, as a refresher, where the RF profile gets applied is in the AP group. So let's go and look at that real quick so everybody's aware of it. So let's go to WLANs, and we're going to go over to the left and click on Advanced and AP groups. So I've created this AP group here called Lab. And in this AP group, I have one of my 3 APs. So I have this AP in this AP group. So all the settings that I'm applying to the AP group apply just to this one AP and not the other 2. You can see in here, you can specify your WLANs, and then the important thing I want to point out is the RF profile. So this is a really granular way to group APs together and give them specific RF settings for the area that they're in. And so that's where I've applied that 5 gigahertz RF profile that now has the bandwidth selection set to best. Additionally, I'll show you how to set it on a global level. So let's go back to wireless. And we're going to go on the left to the 802.11a network, and we're going to go to the DCA. Now, see the same setting here, however, it's still set to 20 because that was a global setting. I set it in the RF profile. Since I have it on my RF profile, that overrides the global setting for any APs in my RF profile. But let's just say I want to change this to best. I'm going to hit apply, and you'll notice I'm going to get an error saying we can't change this because your network is still functional, your 5 gig network. So this is one of those settings in our controller where you have to turn off the 5 gig network completely to make the change before it'll take it and save it. That's the other benefit of using RF profiles is we don't have to bring down the whole 5 gig network to change it in the RF profile. It makes the change and just resets the radios of the APs that are in the AP group for that RF profile. So this is another benefit of using RF profiles I want to make you aware of, and where you can change the setting globally. Back to you, Jason.
Love it. Yeah, thanks. I appreciate that. So, another thing that we can use the same technology for, or a similar technology for, is something called event-driven RRM. So our clean air chipset, that's just a fancy word for putting a spectrum analyzer built into the chipset, not on the left-hand side of the radio, but really built into the radio. That gives us the ability to see at a much more granular resolution, frankly, than is required to serve Wi-Fi. But the idea is that with that resolution, we're able to act on catastrophic interferes that may only be around for like 45 seconds at a time, like when a microwave oven uses 2.4 gigahertz energy to activate the water molecules, causing them to vibrate, causing friction, right? Causing my frozen burrito to heat from the inside out rather than in a regular oven from the outside in. Now, if my microwave oven is not properly shielded, which happens from time to time, it probably isn't going to cause some sort of like catastrophic health event on me, but it certainly does cause a catastrophic event on our Wi-Fi network. Now, we can detect these, and event-driven RRM not only detects this from this event happening, but also can mitigate them. Another interesting thing, Alan, I know you have a really great example. Can you show us your great example?
Yeah, so I have exactly what you see on the screen here with me. It's a camera you can get off of Amazon. It is $20 and it runs on a 9-volt battery. And guess what? It runs smack dab in the middle of that 2.4 spectrum. The funny thing about these cameras is they have a 100% duty cycle once they start transmitting, and they don't stop until you power them off. That 100% duty cycle causes the AP to stop beaconing and all the clients to stop communicating on the channel or spectrum that the camera is actually on. And we're going to do that right now, and I'm going to show you what that looks like. Before we start, though, we got to make sure we have clean air turned on and our event-driven RRM. So I'm going to go back to the home screen, and we're going to go back to the best practices we have here. And under RF management, you'll see clean air detection here, and it is not enabled, and you can set it up here to enable it. And you can also see the event-driven RRM is not enabled, and you can also enable it here. However, we're going to do this in the advanced screen to show you guys where that's at as well. So let's go back to wireless, and we're going to start with our 5 gig network, 802.11a, and on the bottom of that, you'll see clean air, and we'll just check this box. Leave everything else the way it is. That's that simple, and we'll apply that. And we'll do the same on our 2.4, our 802.11b network. We'll turn this on. All right, so now that we got clean air enabled and we're scanning through the APs, let's go enable event-driven RRM. So under DCA for the 802.11a 5 gig network, at the bottom, you'll see the event-driven RRM. Here, we'll check the box, and we have the options for our sensitivity. Now, the sensitivity is tied directly to the air quality score that clean air uses. So for low, the air quality would have to get down to 35 to trigger a channel change. For medium, it'd be 50, and for high, it'd be 60. And of course, you have the custom to set whatever you want. Now, low is a low air quality of 35 is pretty bad. If you move it up into the high range, or if you do custom and you get above 60, you're going to be making channel changes immediately when you see things like Bluetooth and Xbox controllers and other stuff that's in 2.4. So you want to be careful with this and not set it too high, because you'll be making regular channel changes off schedule when you start seeing these kind of minuscule events. Really, the Bluetooth isn't that impactful, so I wouldn't say that's a reason for our event-driven RRM to actually make channel changes. So we're going to set it to low today and show you how bad this camera can impact the spectrum. And a new option that's been added recently in the code is a rogue contribution. So we can actually look at duty cycle from rogue APs, and if they have a high channel utilization or duty cycle, we can move away from those channels, because it's more likely that we're not going to see the rogue stop doing that. So it's just better to get the clients and the AP off to another channel while that rogue does whatever it needs to do, and we can mitigate that by removing it or just staying away from it altogether. All right, so now that we got it turned on for 5 gig, we're going to do the same thing on our 2.4. So we'll go to the BGN network, go to DCA, and enable event-driven RM. We'll leave it at low, and we'll do our rogue contribution, and we'll apply this. All right, so to validate this, we're going to go over to the monitor tab, and we're going to go on the left clean air. You'll see you have the 5 gig and the 2.4. We're interested in 2.4 today. So we'll look at interfering devices.
This is the cool part, right? This is the cool part.
This is when it gets fun. So we don't see anything yet. Yeah. Hang on. Let me make sure we've got our clean airs enabled. So wait for it to come back up here.
You failed your interference profile.
Yeah, should be seeing something. Make sure I set this right. Yeah, all right. Give a chance for the clean air to come online here.
Right.
This is the way live demos go.
Right. Here I just got all excited about something. Sorry. Your operational status is down on all APs.
Yeah, I see that. The clean air. I turned it on.
Thank you, Greg and Ollie, for seeing that.
All right, let's go take a look and see if it's on yet. Please.
Please.
Please come up.
Down, down, down.
All right, well, we may have to skip that one today. We will try and come back to it and see if it comes up.
Yeah, well, we can come back to that one. Maybe that can be the bonus at the end.
For sure. All right, so let's go.
What we should have seen though is an interferer, and we would have seen the full impact of that, right? Well, we'll come back to that.
Yeah.
Live demos, right? This is not these aren't low, flash runtimes. Next thing we want to do, changing gears a little bit, is talk about something called fast transition or BSS fast transition, also known as 802.11r. Now, although this is a standard, there is some things that we've done that's a little bit different, a little bit special. So let's take a look at that. Okay, so here I have two Cisco access points, AP1 and AP2. What fast transition does is it enables a roam to happen without a full 802.1x authentication. You'd think, well, wait a minute, that's not exactly brand new. It's not, but we've done it in the past using proprietary mechanisms. Now we have 802.11r. That is a standard-based mechanism for do that. So as we see the roam to a new AP, we don't have to fully re-authenticate. Alan, are you, okay. Sorry, I was just going a little bit slow. So let's go look at another example. On the left-hand side, I have a non-Cisco access point, which means that if I have 802.11r turned on, then devices that don't support 802.11r won't be able to connect to that SSID at all. However, on the Cisco side, during the authentication, 802.11r is recognized, hey, you're an Apple device, which does support 11r. I'm going to enable it for you. However, if you're a legacy device, I'm going to recognize that you don't support 11r. You're able to connect to the same SSID, and now we're able to conform to a lot of the best practices, Cisco and industry best practices of limiting the number of SSIDs, but still allowing things like 802.11r and Fastlane, which is some really cool stuff that we've done jointly in development with Apple. So that is 802.11r. Alan, let's check it out. What does it look like?
Sure thing. So what I'm going to start with here is I have a iPod, and it has this handy app. So all iOS devices running iOS 10 or higher can run this app. It's called the Fastlane app. and it will detect for those 11R, adaptive 11R frames and tell you whether it's turned on or not. So I'm going to bring it up here, and you can see I've got the guest SSID I'm connected to here, and in fact it's showing that I don't have those 11R frames visible for the iOS device. So I'm going to come over here to my guest SSID, number 17, and it's as simple as going to the QS tab, and there's a new feature called Fast Lane here. And so what we want to do is we want to enable that. It's going to tell us it's going to reset a few things if you already had them set. So we're going to say OK to that, and then we're going to hit apply. And what it'll do is it will disassociate the client, and once it reassociates, we should see it say green and that we are seeing those frames. So let's wait for it. And there we go. So now we're back on the guest SSID with it enabled, and you can see the iOS device is actually seeing those 802.11r adaptive frames in there. Simple as that. It's a pretty easy feature to turn on. Back to you, Jason.
Love it. Love it. Thank you. The next thing, I'm going to use what might look like a little bit of a cheesy explanation to show you what airtime fairness is. And what I'd like you to do is just for a moment suspend yourself from the industry that you work in, and I want you to think about you living in or working in the healthcare industry. Unless you already work in the healthcare industry, in case don't pretend you're already there. So in a healthcare industry, you're operationally your business runs on an electronic medical record system. And then, of course, because you're a hospital, you also allow patients to bring their clunky old laptops to connect to the same network on the guest side. But, see, you're smart. You have implemented a QoS policy that says you're only allowed to use a certain amount of bandwidth. The problem is those clunky old laptops might not be able to connect at the highest data rates. And so they're going to use that bandwidth, but they're going to use it really, really slowly. And because only one device can talk at a time, that leaves less time for the fast talkers to talk fast. So with airtime fairness, we actually say, well, you know, those old clunky devices, yeah, they have a bandwidth contract, but they also have an airtime contract that says they're only allowed to talk for a certain amount of time. So if there's contention for bandwidth, then we're going to limit how much time that those devices can talk, leaving more time for the critical applications. Alan, can we look and see how we turn that on?
Absolutely. Let's take a look at that. I think I have the answer to why we were not seeing the clean air, and it was thanks to one of my colleagues. I didn't have the 2.4 network enabled. Derek, you're a savior, buddy. So now that we have this, we're going to run through the demo of clean air, and then I'll jump into that airtime fairness. So we catch all things. So let's go back to our clean air on monitor, and now we're seeing some clean air data. Before we start this, what I am going to show you is what channels we have our APs on. So right now we have channels 1, 6, and 6 for my APs that I have here. So that should even out into 1, 6, and 11. Since I just turned the network on, they're going to figure it out right now. But what I'm going to do is I'm going to try and chase this one AP off of channel 1 with this camera. So let's go back to monitor, and we're going to go to clean air, and we're going to go to interfering devices. So let me set my camera to channel 1, and I'm going to plug it in, and we're going to look and see what happens. All right. So just plugged in my camera. And I'm just going to click on this to see how fast it updates. And you can see here shortly we will have a video camera.
On your Xbox.
No, it's not Xbox. It'll show up as video camera.
No, it found your Xbox.
Oh, yeah, I don't care about the Xbox.
I like how it gives me a severity number. That severity number is between 0 and, 99, I believe. Yeah. And, oh, no, it's between 0 and 100. Oh, yeah. The severity. It's 100% duty cycle. Found your camera.
Yep. So there's our continuous transmitter. We're going to give it a chance to show the severity here. So 84. And it's impacting a little bit wider than just the single channel. So what we'll do is we'll go back to the APs, and let's see if that AP has already moved off the channel, right? So it's moved immediately once we see the interference because the severity was so bad. And just to go back to the clean air and look, right, so we still see the continuous transmitter. If we look at the air quality graph for this, we should see we, in fact, did meet that watermark of 35. Remember, I set it to low, and that number equals 35 in the air quality. So we made it below, well below that number, which is the reason why event-driven RM triggered the channel change instead of waiting for the 10-minute or 1-hour interval, whatever you have it set to make that channel change. So cool thing about event-driven RM is we can make changes immediately on top of clean air giving you information about what's happening and notifying you in the form of traps. All right, so let's jump into, let's go and disable the 2.4 network because nobody likes 2.4 as we finish this off. And let's go into airtime fairness. All right, so airtime fairness is found in the wireless tab. Over on the left, you'll see ATF. And what we're going to do first is we're going to turn on the monitor mode so you can collect statistics. This is probably one of the first things you want to do to figure out what's going on with the airtime usage. You can do it as specific as an individual AP group, or network as a whole. I'm going to do the AP group today, and then you'll select your spectrum you want it to use, either the 5 gig or 2.4. Simple as that. You hit enable, and so now we have APs collecting those statistics. So what I'm going to do here is just to pump some traffic through. I've got some devices that are connected, so we're going to run some speed tests and see how these guys perform with no airtime fairness in place. So we're going to run the iPod first against the Android. They're both connected to the same SSID. I have roughly about 100 meg of internet here. So you can see once the Android's got it, the iPod's going to struggle with getting some until the Android stops talking. Now, again, ATF only works in the downlink direction. We can't control who talks at what time with the clients. So in the uplink, you'll see contention, but the downlink is what we can schedule. All right, so I'll let that run, and then I'll do it one more time here once that one finishes. I'll do the Android first. Again, you get about 100 meg. iPod sits there and struggles because the Android's stomping everybody. All right. So now we got some statistics in there. Let's go back and let's take a look at the statistics. So again, in wireless menu on the left under ATF, there's statistics. And there'll be a drop down for the individual AP that you want to see the statistics on. And you'll be able to come in here and see, kind of how the airtime is slicing up and the performance of it. So once you've got a good grasp of where things are and how things are panning out with usage, you can then decide how you want to set your policy. And we'll start with the policy configuration. You'll set your policy weights. I've set 2 here. There's one by default 0 that comes out of the box. I've done one at 5% and the other one at 95. Making a new one is as simple as selecting the ID for that one, putting in the name you want, and then putting in the weight that you want to give it. You have an option for client fair share now as well. So within this policy bucket, all the clients will get an equal share of that bucket as there's more clients that come on. So no one client can actually take all of it like we were seeing before. So we can turn that on as well. And then we'll hit create, and it creates a new one. If we need to go in here and modify an existing one, we simply select it and make the changes we want, and then hit modify. So now we got our policies. We're going to put them into an enforcement mode. So we'll go into the enforcement mode menu, and I'm going to again select my AP group. And then I'm going to select my band. So we're just doing 5 gig. And you have the option of optimize or strict. Optimize means it will take airtime tokens from other buckets if they're available. Strict will enforce the policy exclusively and not take extra tokens from other policies if they're available. So you can decide on which one. So if the airtime's open and you've set your guest net to, say 5%, it'll take tokens from the other policy if the tokens are available to use. So we'll click on Enable once we've set those. And now you'll see down here at the bottom, we have a AP group level policy in place. And to validate it, we can go look at Lab and click on the link, and we can see my policy is 5% on SSID 1 and 95% on SSID number 2. If we wanted to change that, we would come in here and select the AP group, select Lab. We would select our SSID ID, so that would be 17 would be guest, and if I wanted to say make it 50% of my policy, and then we'll select the radio and click Add. Now when I go back into that lab, you should see it's selected now the 50% policy instead of the 5. But I want it to be the 5, so we're going to go back and change that. We'll do lab, do the SSID. We want 5%, and we want it on the 5 gig network. Hit add, and then we'll validate it. And so now we're back to the 5% for my guest and 95% for my corp. Okay, so now we got that in place. Let's go back to our devices and see if there was any impact. Again, this is not too scientific tests. Your results will vary depending on clients and RF environment, but let's just give this a wash and see what happens. So you see the iPod's getting a little bit better share. We'll give that a run, another run, and see what happens with the iPod if it goes first. It's easy to see the contention on the uplink side because there's no way to control that, right? So I'll let the iPod finish. We'll run this one more time. We'll go back to our stats. All right, so we'll test this again here. That guy will take off and get a lot of share. And here comes the Android, and so the iPod's getting backed off to give that equal share to each other. Now, the tokens are based upon millisecond time slices and what the capacity is of each device from a throughput perspective. So depending on what their actual data rates are is part of the calculation. So that's why I say the mileage varies depending on what the data rate of the client is and what the RF environment looks like and how much air there is. But it's an easy way to see there's some changes going on. So if we go back to the statistics, again, we'll get statistics coming off this from the enforcement mode as well. You can see in here we're getting packets dropped because we are enforcing that airtime entitlement and keeping them at capped at 5%. And that's how you set up ATF.
Hey, Alan, question came in. What's the difference between airtime fairness and the override per user bandwidth contracts in SSID, within the SSID config?
It's a good question. So in the SSID config, you're referring to, if we go to WLANs,
right.
Pick one of these here. If we go to QoS, you'll see we have options for doing bandwidth rate limiting. This is actually going to rate limit the amount of traffic we pump out of the controller from a networking perspective, but not how much airtime they have entitlement to from the medium, from the channel perspective. So if we set this to, let's say, 5 meg, that means if I've got a large volume of data for this one client and they can only go 5 megabits per second, they're gonna hold up that channel while they try and finish that 5 megabits per second. Whereas if we do airtime entitlement, we can actually tell them to get off the channel because they've used so many of their tokens, their millisecond tokens. We'll get another client on, even though they haven't finished their download, and we'll move back and forth between those clients to finish out their tokens, or we'll drop their traffic altogether if it gets exceeded. Makes sense? So this is a networking level bandwidth restraint. And airtime entitlement or airtime fairness is a layer 1 level constraint where we can actually control access to the median itself. All right.
Great, thank you. That's a great answer. I think so. Let's hit up the next topic. So. The next topic is RX-SOP, and RxSOP is it stands for Receive Start of Packet. Let's describe it first. First of all, this is a super high density environment. I have a picture of just like a ton of desks, and it has a lot of access points in this area, but I'm just going to show you a couple of them. So here's one AP I put up in the corner here, and I'm going to color its coverage area white. Now, down the hall, there's another access point that, because of just a limited number of channels, it's also on whatever channel white is. Now, there's a computer here. It's connected up to the access point over on the right, and the access point says, hey, you're connected, I can hear you well, everything's great. The problem is the other access point on the same channel, oh, I can hear you because I have really good receive sensitivity. And now, of course, since only one person can talk or at a time, right? If there's a client talking, the access point can't talk. And it goes, hey, you're on my channel, so I have to receive the whole packet before I realize, oh, I'm not even supposed to be receiving this packet. Hold off, everybody. There's this loudmouth down the hall. And now I'm contending for basically spectrum availability with the client that's down the hall. In comes this thing called RX-SOP. It has such a bad name, I thought I'd create a logo for it. So here's a cool logo, RX Receive Start of Packet. Still not very obvious, right? Well, here's with RX-SOP, I've got my access point in the corner. I'm connected to it. I can still hear you well. But that access point way down the hall, are you moving forward? There you go. So that access point down the hall is basically saying, hey, you're not loud enough, I'm going to ignore you. So even though you're on the channel and I should be listening to you, because I can't hear you loud enough, I'm going to ignore you, and I'm going to serve the client devices that are closer to me. So that is Receive Start of Packet, or RX-SOP. Alan, can you go into a little bit more details about this?
Yeah, I mean, there's really the points to make here is that this is blinders for your AP, right? So when you set these thresholds, when you make these settings and turn this on, you're telling the AP to ignore anything past these numbers. So these are very important numbers to keep in mind when you're setting it. Generally, when you set it to low, most environments can see improvement. As you get into the high settings of the thresholds, be careful, because you're going to exclude not only the APs down the way, you're also going to exclude your clients. You're not going to talk to anybody if they don't meet that threshold. So be very careful with this. Again, this is run it in your lab, understand it completely before you cut everybody off. So let's take a look and see where that setting actually is in the controller. This is another great one I like to do on RF profiles. So we're going to do that under Wireless RF Profiles. And we're going to go into the high density tab for my 5 gig RF profile. And you'll see the RX-SOP threshold here. It's set to auto by default, and then you have your options for low, medium, and high here. So you can set it here and then apply. You can also do it globally. So if we go into the 5 gig network and then go to, it's actually in the advanced. If we go to the RX-SOP threshold setting, we have the global setting for both 5 gig and 2.4 there as well. Pretty straightforward, not much else to configure there. And it's a little more difficult to show the benefits of it without some specialized test setups to see the utilization come up or to see improvement in clients. So this is start low, be very conservative, and then see how your mileage goes. If it gets better, then leave it there, and then see about tuning it later down the road.
Awesome. Thanks, Alan. Hey, the last feature that we want to talk about today, certainly not the last feature in HDX, but the last one that we want to focus on, is called optimized roaming. And so optimized roaming sounds great, right? But the thing to remember is that client devices are responsible for determining when to roam and where to roam. And regardless of how smart your infrastructure is, it's still ultimately the client that makes that decision. Let's look at an example. So here I have a kind of a floor plan, and I'm designated 3 access points just for the sake of just explanation. So I'm going to connect a device. I'm going to use my iPhone here. So I connect my iPhone, and as I move around, the client device stays connected to AP1, right? Because it hasn't determined that it wants to roam yet. Now, even though I'm not necessarily close to AP1, I can still kind of hear it. And that's really the problem because I still haven't determined to roam yet. So as a result, I get just like a single bar of connectivity. Let's show what that looks like, right? So now, as I move around and I get further away from the access point, I finally do roam. Here's the problem. I'm sitting here. This is me. I started my day in one corner of the building, and then I go to a meeting in the other corner of the building, and I'm frustrated because I have my one bar, right? I look at my phone, one bar of connectivity. This is lame, and I look up, and my frustration grows when I realize that I'm literally underneath an access point. And this has happened so much. I recognize, oh, hey, I know how to fix that. I turn Wi-Fi off. I turn Wi-Fi back on again, and oh, hey, look, it's fixed. This is called client stickiness. And we fix this with something called optimized roaming, or HDX optimized roaming. So with optimized roaming turned on, the infrastructure sees the client moving around in RF space and recognizes that it's gone to the edge of one cell and into another cell. And the system itself can actually send a message to the client device, hey, roam now. And so as it roams, you are connected to the access point that's closest to you. As a result, you'll be able to connect at the highest possible data rates, which is great for me, but it also makes me a better Wi-Fi citizen because if I can say what I need to say really quick, that means that there's more time for other people to say what they need to say. So this is called optimized roaming. I'd like to hand it over to Alan for the fine print.
So some very important things to know. Optimized roaming shares thresholds with coverage hold detection. And again, if you use RF profiles for some of those settings, they override the global values. You have to have coverage hold detection turned on the WLAN for this to work. If coverage hold detection is not turned on in the WLAN, optimized roaming will not work. The client, we use client RSSI and data rate for disconnection thresholds. So we can use either or one of them. Optimized roaming disables data coverage hold detection. So data RSSI coverage hold detection gets disabled when you enable optimized roaming. However, the voice coverage hold detection still works. And once clients are disassociated from the AP using optimized roaming, they need a 6 dB gain for them to reassociate. So an example, if we have an negative 80 as our threshold for optimized roaming, the client would have to be up to negative 74 to reassociate. So very important things to keep in mind as you're going through this. So let's take a look at some of the settings on our final feature, and we'll go through this pretty quick. We'll go check the coverage hold detection on our WLAN just to show you where that's at. It's under the advanced menu, and you'll see it here at the top. We have it enabled, so coverage hold is on. We'll go into the global setting for optimized roaming, so that's under the advanced. And let's go to optimized roaming. And we'll see we have both setting for each spectrum. We'll turn it on. And it's going to tell you you're going to mess with coverage hold detection settings, not a problem. And then you'll have an optimized roaming interval. So it's set by default 90 seconds. And then you can do your data rate as well. So if you want in 90 seconds that they fall below neg 80 and they meet this data rate threshold or fall below it, then they're going to have to get booted and move on to another AP, hopefully. So some of the other values you can set are going to be under coverage hold detection. You'll find those both in the RF profile. I'll show you where those are at right now. So look at RF profile here and under RM. So we got our coverage to hold detection settings here. So this is our value. So it's default neg 80. We could set it to something higher or lower depending on what fits the environment, what you're trying to do. And then the coverage level exception. So what we're saying here is if 25% of 50 packets are at or below neg 80, we're going to tell the client to get lost if we don't use the data rate as part of this coverage hold detection calculation. In the global settings, these values land under the individual radio band. So under 802.11a, the 5 gig, go to coverage. You'll see the same settings here. For the data RSSI, it's neg 80. We could set it here as a global level, not at the RF profile level. You have the 25% for the coverage level exception as well, and then the data packet count. So that's where you make these changes, and you can turn it on and see how it impacts your clients. Where you validate that is in the monitor tab under statistics, and then you'll go to optimize roaming, and you'll be able to see whether these counters are actually incrementing.
And what's the command that the client actually gets?
They'll get a disassociate command.
Okay, awesome.
Yeah. And that's our final feature.
That's awesome. So thank you so much, Alan, for your time today, and everyone, thank you so much for your attendance. I appreciate it. And hanging in there with us. This is a lot of information. I know sometimes I feel like it's throwing spaghetti at the wall and seeing what sticks. However, please know that this recording will be available to you, and as soon as I get it, I'll get it posted up to the Wireless Friday landing page, which is at cs.co/wirelessfriday. If you are not subscribed, please click on that big blue subscribe button. You'll get 2 emails a month. One the week of, reminding you that it is Wireless Friday week. One the day of, saying, hey, it's Wireless Friday, the event will start soon. I promise that's really the only thing I'm going to use that for, so not going to be signing you up for a bunch of spam. It is the 4th Friday of each month, so that means May 26th, June 23rd, and July 28th. Looking forward to those. We do have a topic list that's kept up to date on the Wireless Friday landing page. However, if something really interesting comes up mid-month and I want to change it, I might just change it. So know that it will remain relevant. So anyway, hope all is well with you. Thank you so much for joining us, and have a great rest of your Friday. Happy Wireless Friday, everybody. Thanks.